Supermassive black holes are the most continuously luminous objects in the known universe. For a post-biological intelligence seeking to maximize its processing capacity, these accretion disks represent the highest accessible energy density in existence. Historically, the progress of a civilization has been measured by its energy consumption. As technological needs scale, a society eventually exhausts its home planet and local star, forcing a move toward larger, more efficient power sources. Because computation is physically limited by available energy, the logical endpoint for an advancing mind is the galactic center. This is the Dyson mind, a computational infrastructure built to harness the output of a central black hole. This infrastructure spans parsecs, intercepting radiation that outshines entire galaxies. These Dyson minds operate under the same gravitational and thermodynamic limits as our own technology, transforming speculative concepts into a set of solvable engineering problems. Thermodynamics, orbital mechanics, and information theory dictate the exact physical architecture of a Dyson mind. The extreme environment of a galactic center leaves no room for arbitrary design. These immutable constraints force the intelligence to interact with its environment in predictable ways. To harness power and reject heat, it must produce distinct signatures that contrast with natural astrophysical noise. Identifying such a system requires isolating specific structured deviations from the expected behavior of a natural accretion disk. By modeling the physical limits of extreme computation, we can predict exactly how an artificial structure would distort the data currently recorded by our telescopes. Constructing a Dyson structure deep within a supermassive black hole's gravity well introduces severe mechanical realities. A rigid, contiguous shell would succumb to gravitational instability and catastrophic shear stress, shattering under the varying pull of the central mass. Structural survival requires a decentralized Dyson swarm. However, millions of distinct objects in close proximity create the risk of a Kessler cascade, a runaway chain reaction of debris following a single collision. Avoiding such a cascade requires continuous, precise orbital station keeping for millions of individual nodes. Propulsion for this maneuvering can be harvested directly from the environment, using radiation pressure from the accretion disk to offset the pull of gravity. The swarm might also engage in gardening, intentionally manipulating the orbits of nearby stars to direct them into the black hole. This process stokes the accretion flow to maximize energy yield while actively suppressing the formation of destructive relativistic jets. A Dyson mind is a violently active, mechanically precise swarm that must perpetually outmaneuver its own destruction. Every calculation performed by the swarm generates entropy. This must be radiated away into space as waste heat. To prevent the hardware from melting, the computing nodes must maintain operating temperatures between 100 and 3000 Kelvin. Inner orbits maximize harvested energy density and raw computational power per unit of mass, but the intense UV and X-ray flux near the event horizon rapidly ablates physical materials. Moving the swarm outward to the dust-obscuring region provides safety, but drastically reduces accessible power. Survival in the high-flux zones might require self-regenerating sacrificial shielding layers to absorb the brunt of the radiation. The final configuration of the swarm is a thermodynamic compromise between processing power and material sublimation. For a swarm spanning a parsec, the finite speed of light becomes a barrier. A signal requires over 3 years to cross the structure. The Shannon-Hartley theorem limits the maximum data rate of electromagnetic signals through a noisy channel. Transmitting zettabytes of data via radio or lasers becomes impractically slow at parsec scales. The Bekenstein bound suggests an alternative, encoding massive datasets directly into high-density physical matter. In this regime, it is more efficient to launch physical mass couriers on eccentric orbits to manually transfer data between computing nodes. While travel times are measured in years, the total throughput of physical mass transport vastly exceeds electromagnetic transmission. At galactic scales, physics dictates that throwing a physical hard drive across a solar system is faster than beaming the data. This latency makes a tightly synchronized, unified consciousness physically impossible. Instead, the mind must exist as a sparse, distributed federation of semi-autonomous subminds. Operations follow a map locally, reduce rarely paradigm, the only viable operating system for parsec-scale structures. Evolutionary algorithms allow local nodes to solve isolated problems, only merging their results when orbital geometries allow. A Dyson mind is an ecosystem of isolated processing clusters, constrained by the speed of light. We can search for these thermodynamic and architectural compromises using modern astronomy. The inescapable signature of a megascale computer is massive, highly localized infrared waste heat. A swarm operating at 100 to 3000 Kelvin will reshape the host galaxy's spectral energy distribution, adding a smooth blackbody curve peaking in the mid-infrared. This artificial emission will dilute the specific silicate and hydrocarbon features usually produced by natural dust. The mid-infrared instrument on the James Webb Space Telescope is specifically designed to detect these wavelengths. Isolating these signals requires running anomaly detection sweeps through archival space telescope data to find color space outliers. A Dyson mind cannot hide its entropy. Its waste heat provides a glowing beacon in the mid-infrared spectrum. A secondary signature comes from the geometric occultation of the accretion disk by the swarm infrastructure. Massive nodes orbiting directly in front of the inner accretion disk will geometrically occlude these high-energy background emissions. Unlike chaotic natural variability, swarm transits produce sharp, non-stochastic square wave dips in the light curve. This methodology follows the logic used to identify unnatural orbital behaviors in recent exoplanet transit studies. Reanalyzing archival Event Horizon Telescope polarimetry data could reveal these coherent absorption patterns. Searching for intelligence on a galactic scale shifts from intercepting messages to recognizing the inescapable mechanical and thermodynamic footprint of megascale engineering.